Welcome back to Inorganic Chemistry. In this lecture, we'll cover the chemistry of the main group elements. So the main group elements, of course, are the groups 1 and 2. They have the A in the American nomenclature. We skip the transition metals and go through the groups 3, 4, 5, 6, 7, and 8. But before we talk about these main groups, I want to go over in this part of the lecture the guiding framework and talk about how hydrogen fits, or rather does not fit. So to remind you, the periodic table discovered in 1869 by Mendeleev. According to his own account, he had been moving around cards describing the elements and their properties on a table and trying to understand their relationship, and he dreamed about how these cards could be all laid out according to weight originally. Now we use atomic number. So interestingly, while the guiding, organizing principle of chemistry was being developed in 1869, the guiding, organizing principle for biology, evolutionary theory, was published only 10 years earlier in 1859 by Darwin. So to remind you about trends in the periodic table, we know that from before we've seen how the ionization energy increases across a period. Electronegativity increases across the period, and electron affinity increases across the period. So going up a group, these properties also increase. And the opposite trend, radius increases as we go right to left on a period. Radius increases as we go down. We can also discuss the periodic table in terms of the blocks. So the main group elements in the green here, blocks are when the s and p orbitals are getting filled, and that's what we're going to focus on in this set of lectures. The red highlighted elements here in the center are called the transition elements, and that's where the d orbitals are getting filled. And then the blue block here highlighted, the lanthanide and actinides, are where the f electrons are getting filled. And on the playlist I've included a YouTube video by someone else that describes how actually lanthanum and actinium probably are not the correct elements for these spots right here. We already talked a little bit about how to organize these main group elements, or what's called descriptive chemistry. So descriptive chemistry is where we describe the chemistry of all the different elements. So that's a lot of facts that have been collected over hundreds of years, and we could be here all day. So to help kind of frame our discussion, we're going to use these guiding principles. So first, the periodic law. We just discussed the periodic trends that we already know about or familiar with the periodic table. Another principle we're going to look at is the uniqueness principle, which has to do with the first row of elements, the diagonal relationship between the first and second row of elements, the inert pair effect, which becomes important in the fourth and fifth rows, the metal-nonmetal line, hopefully you're familiar with that also from general chemistry. We already talked about acids and bases before, and now we'll see how that fits the character of the elements. Standard reduction trends, we've talked about standard reduction potential in our lab portion of our course, so we'll see how that fits in the periodic table. And then p-pi, d-pi bonding, I'll explain what that means when we get to that part of the periodic table, as described in the book by Rogers. So let's start right away talking about the simplest element, the most abundant element in the universe, hydrogen. But it's also a problematic element because it doesn't fit the periodic table very well. Often it's shown as part of group 1A, but as we can see in this table of the properties of the elements, hydrogen group 1A would be above lithium, but its atomic radius is much smaller than any of the elements. Its ionic radius, of course, would be extremely small because hydrogen just has one electron. You remove that electron, and all that's left is the proton, the nucleus, which is orders of magnitude smaller than this is the ion hydride ion. We can add an extra electron. The electronegativity is between that of lithium and fluorine. The charge density of the ion, of course, if it's the proton, it's much more dense charge than an atom or any ion could be. And then here's the hydride. So that starts to look like these other elements. Let's see. So oxidation state, it can be +1 or -1. Ionization energy is closer to that of fluorine than lithium. Electron affinity is closer to that of lithium than fluorine. So really it's kind of exactly in the middle, depending on which property you look at, or even in some cases exactly in the middle of the properties. So some periodic tables have hydrogen by itself right in the middle. Now, what are some chemical properties of hydrogen? Actually, these are the nuclear properties of hydrogen. It occurs in 3 different isotopes, where protium is the one we're most familiar with, and it's by far the most abundant. Deuterium is actually slightly abundant in nature, and we use deuterium, enriched deuterium, for compounds for things like NMR solvents. If we're doing proton NMR, then we don't want the solvent to overpower the sample. The sample has the proton in it, or the hydrogen in it, so if we use deuterium for a solvent, we won't see it. Tritium is important in nuclear fusion. Both in the sun and also in possible experiments on Earth. What are the compounds of hydrogen? Covalently, we're very familiar with these types of molecules: water, methane, other organic compounds. And since the electronegativity of hydrogen is very similar to carbon, this forms a very stable covalent bond. When it's in these molecules, has a formal charge of +1, but when it's in an ionic compound, it's actually considered a hydride, or a formal charge of -1. And calcium hydride, as an example, is very reactive with water, but in a gentle way. So we actually are going to use calcium hydride in our lab to remove water from organic solvents by this reaction. Hydrogen can also make metallic bonds with metals such as titanium, and this compound here you see is non-stoichiometric, and that's because the hydride ion is occupying interstitial sites in the titanium metal lattice, and these type compounds are important for hydrogen economy because it could be used to store and transport hydrogen.